Okay, you can see the agenda okay now?
Yeah.
Okay, let's get started here. We have about 30 minutes, so you have to take your notes in shorthand because we got a lot of material to cover. Some of you may not be familiar with Sinda. I glanced through some of the names of the attendees, and I see some familiar names, so I know some of you are Sinda users. There's a few flavors of it floating around, and there's a few type of codes like Sinda that are used in the world today in Europe and in the U.S. that are network thermal analyzers, as opposed to the traditional finite element thermal analyzer. So Sinda basically solves like an electrical network analogy to a thermal problem, and this method is a method that was actually developed 50 years ago during the Apollo program at Chrysler Aerospace, and it was spelled CINDA for Chrysler Integrating Numerical Differentiating Analyzer. And later in the 70s, when NASA picked it up, and Jerry Gaske, who wrote the first Sinda, went to work on that at TRW, they changed it to Systems Improved Numerical Differentiating Analyzer. So it's an acronym, and it started about the same time NASTRAN did. NASTRAN was a finite element code used for structures, and Sinda was a finite difference lump parameter network solver. And many people in the aerospace world today still use Sinda. Here it's 50 years later, like NASTRAN has gone through about 50 years also of development. So it's far different product today than it was then. Every year we keep adding features and it keeps getting better. But our roots go back to Jerry's original code back in the 62 and NASA's version in 72, and he started a private company in the early 80s. That's when I switched from the NASA version to his version and got involved with development on Sinda. So it's been around for a while. It joined network analysis in 2008, and the key that keeps Sinda alive today is it's more than a thermal analyzer. It's really a powerful thermal programming language. And thermal people who do more difficult thermal problems, not just real simple ones, they tend to need some extra features. They need to put in some equations, some if-else-then logic, because the boundary conditions are usually pretty messy. So the nice thing about Sinda is you can literally teach someone how to add equations and programming logic in just a few hours. We have a 4-hour class where we teach people how to add subroutines and equations for transient steady-state models, and after a few hours they're pretty comfortable with that, and you can show someone in a couple minutes how to add a simple equation. Also, Sinda is pretty intuitive. It follows the concepts and heat transfer textbooks, so building simplified Sinda models before you get into a more detailed model that's meshed in Patran or something gives you some real physical insight, because you see conductors that model like watts per degree C, and you see thermal masses that are like watt-seconds per degree C. So something's 1,000 watt-seconds per degree C, and you put 1,000 watts into it for 1 second, it's going to rise 1 degree C. So you can just look at a Sinda model and see what gradients are going to be based on heat flows, and you can see how fast thermal masses are going to respond. And we have a tool, Thermal Studio, you see on the right panel here, that people use to build simplified models to get started with. And but it also transparently integrates into Patran, and we have a way of integrating it into SimX also for those who use those sort of modeling tools. Some of the applications that Sinda is widely used for, things like aero heating, ablation, phase change, aircraft anti-icing, spacecraft thermal, electronic equipment, whether it's chips, PC boards, or boxes, thermoelectric coolers, heat pipes, including variable conduction heat pipes, ovens with complex controllers and multiple sensors, different aspects of automotive thermal. And we're just getting some interest in solar companies modeling some of their power plants or solar heating of buildings and things. So let's look at a simple network thermal model, and this is a side view of an automobile. And we have just a few nodes in our model, plus these square boxes are boundary nodes. We have one for the sky that we radiate to, and we have one for air that we convect to. And we have a solar load that goes right through the windshield and hits the dashboard on a car, and it heats up, and then the infrared energy gets trapped inside and can't get back out through the window. And during a 2-day cycle where the car was sitting out in the sun for 2 days, you can see the peaks here, and we built a simple model just seeing how that dashboard might heat up at a maximum. And then we went to a more complicated model where we had a window, a transparent window, and we had a detailed dashboard, and we meshed it more finely from CAD. And actually we got very similar results if you pick the hot spot on the dashboard and the window temperatures. But we have a lot more resolution here. So we usually recommend starting off with a simple model because it gives you real physical insight into the system. You'll understand your thermal system much better by starting off with a simple thermal model. I was at a thermal conference once, and there's a guy from JPL, and we're sitting in a jacuzzi after the conference was over, and he said, I like to start my spacecraft models with one thermal node. And I thought, Paul, you've been in a jacuzzi too long. I said, how do you do one node? He says, well, I just put all the mass of the spacecraft into one node, and then I have a radiator that I radiate off to space, and I know how much power is in the spacecraft. And by knowing the power and a little bit about the orbit, I can figure out how big of a radiator I'm going to need to get rid of that power. Then I go to a meeting, and they tell me I only have 1 square meter for a radiator, and I can immediately tell them that's not enough with the power that we have. And they think I'm a genius, but I've all done this just from a one-node thermal model. So I don't think I've ever started things with one node, but few nodes. In this case, there's only 6 nodes. Is very common to start off simple models. Here's another example of an electronic package, and you can see this network diagram, and we have Visio and Excel links to Sinda where you can actually build your model by dragging out Visio shapes and hooking them up, and then it automatically builds your Sinda model. But here was the actual hardware, and it was an enclosure here that was hermetically sealed and filled with nitrogen, and inside it had some hard disk, and this went up on a spacecraft. And these hard disks, we had to get the power out of this little frame here through some stainless steel rope isolators, and I was concerned about that heat transfer path because this was shock isolated, so I kind of cut this in half and built 1/2 here just to see if I could get that heat out through those 10 coils in that stainless steel rope isolator, and I saw that I was going to have problems, so I ended up adding at the bottom here some flexible copper braided straps and sized those straps all in this model, ran transient powers and recovery times and things to see what the duty cycle could be on this box for storing data and dumping data, and came up with a design and then went to a detailed finite element model to get the gradients. So it's not uncommon to start with a simple model, which may give you all the information you need, but then you can take it to a more detailed model. Well, today I want to illustrate Sinda by showing you 3 different models. One will be a solar hot water heater. This is a good model because it involves convection, radiation, and fluid flow. And I want to show a spacecraft in orbit and how Thermica transparently integrates into Patran and Sinda. And MSC has our own version of Thermica from Astrium that has our own licensing, and we transparently tie that into Patran so you can use Thermica to compute orbital heating, whether you're orbiting the Earth or whether you're sitting at a latitude and longitude on the Earth for some environmental heating, building or aircraft or car or solar power plant. So we can model things on the Earth or in orbit, and it's a ray tracing code which can model both specular and diffuse bounces of both infrared and visible or UV energy. And I'll show you that. And then the last one will show an automotive application where you could have a radiation shield below an exhaust pipe, and you can have some hot gases flowing down through there and convection from the hot gases convecting to the pipe into the muffler. So let's look at this first solar application. I built some models of like an 11-meter dish focusing on a target like a Stirling engine or something, some parabolic trough that track the sun. The nice thing about Thermica is it can handle kinematic motion like solar panels unfolding, doors opening, closing. You can describe any arbitrary kinematic motion and it will compute the dynamic view factors, the time-dependent view factors, time-dependent fluxes into all those surfaces, and specular bounces off mirrors into tubes of liquid flowing down like this parabolic trough, and this trough then can track the sun with 1 or more degrees of freedom. So we have all those features, and here's an example just to show you solar heating application on the Earth. When I click the mouse here, if the animation works over your web, okay, you should see the sun moving overhead and the solar flux changing and moving across the body of this airplane sitting on the tarmac. And it has actually specular reflections off the sides that are hitting the wing and shadowing and all of that. So that's showing how we can bring in thermal fluxes from Thermica into a Patran generated model. So let's look at this solar flat plate hot water heater. And if we take a diagram and look at this, we basically have a tank, and I have 100 gallons of water in my model, and there's a pump that pumps it up through a solar collector that sits on the roof of the house, and the water heats up as it goes through the collector. And you can have a parallel passageway, which most collectors use. I chose to do a serpentine pattern that goes back and forth just to make a more interesting pattern on the absorber plate. But traditionally, we would use a header on both ends and parallel flow through there to be a little more efficient. Here's basically the things that are involved with a solar collector. If we look at a cross-section of it, there's some glazing here that actually is used to keep this plate hot. It keeps the air from blowing directly on this absorber plate. Some pool heaters won't use glazing. They'll just have usually made out of plastic, a plate with tubes hooked to it, and they don't get nearly as high a temperatures. But when you put the glazing on there, you get this trapped energy in here, this infrared energy, because when the sun hits the black absorber plate and radiates this IR energy, that's transparent plate may be transparent to UV, but it's pretty much opaque to IR. So the IR energy gets trapped in here, or greenhouse effect, and it minimizes our convection losses. And then we have tubes bonded to the back of this with water flow in the tubes and insulation on the back to keep the heat loss out the back. So in our thermal model, we're going to have a solar flux going through the transparent material. Maybe part of it is absorbed, a few percent. Then we're going to have this trapped energy that most of it doesn't go through the glass and stays trapped behind it. We're going to have a small gap here between quarter inch maybe between the absorber plate and the glazing where we have conduction through the air. And then we have some heat transfer off the front of the plate, and I said this was at 45 degrees, so we're going to have a 45-degree angle and natural convection off the top, and then we'll have natural convection off the bottom. And if the wind was blowing, you could have forced convection, but we'll just assume no wind. It's just sitting there in natural convection only. And then we have water flow, and we can model that. We do have a fluids module in Sinda, but we usually use just what we call one-way conductors to model fluid flow, and you just set the value of those conductors to m dot times C sub P, the mass flow rate times specific heat, and that will carry energy only in one direction, because one-way flow conductors only allow energy to move in one direction, so it carries the energy downstream as the energy gets absorbed into the fluid and its temperature increases. So this convection correlation that we used, we have about 44 convection correlations built into Sinda and in our Patran GUI, but a lot of people like to just add their own equations. It's pretty easy to do, but if you want to use one of our built-in equations like this one, which has a Grashof sort of number, Nusselt number, a little bit messy to calculate by hand or put in a subroutine, so we've done it all automatically for you, and all you have to do is specify the length of the plate in this direction and the angle. In this case, it was 1 meter in this direction, and the angle was 45 degrees, and we could hit a little button here, and it would calculate what the core coefficient would be, but this coefficient will be dynamically updated because the natural convection is based on delta T, so it's always changing. The hotter the glass surface or the back surface, then the higher the convection. So we can just attach this correlation. We actually create it as a material and attach that material in place of a constant H value that you'd normally put into a field for a finite element sort of modeler, like Nastran thermal or something. But we have 25 internal forced convection routines, 9 external ones, and 10 natural convection routines. So the flow modeling here, we modeled with just bar elements. We drew some lines, some curves on our plate and meshed it with bar elements, and we set these to be the value to be properties to be mass, flow rate times specific heat of the material, and we set it to have the flow in this direction and do this serpentine pattern. And you can see the cold water comes in at 25 degrees and it's exiting at 33 at the beginning. And we had the plate sitting on the Earth around Phoenix here and tilted up towards the sky, and you can animate that and see as the Earth turns and goes through shadows and things at what time of day it would be, and we get the solar flux into the collector. So let's look at our results. First of all, the solar flux kind of peaks around noon or something during the day, depending on time of year, and then at nighttime it drops to 0 here. And when we looked at the results, we could see that the outlet temperature of the collector started heating up, and up to a peak about middle of the day, maybe 8 or 9 hours later. And the internal temperature in the tank, and I represented that tank. I added 100 gallons of water to one of the nodes, just added mass to one of the nodes, so the tank heats up during the day here and peaks out about this temperature. But now at nighttime, when the solar flux is dropped off, the tank temperature starts dropping, and that's not optimum. You don't want to pump your hot water up on the roof at night. So what we did is we took and added a little bit of programming logic. Basically, as soon as the temperature of the outlet dropped below the temperature of the tank, we turned off the flow. And we could do sophisticated PID controllers with multiple sensors in the tank and up on the roof and different things, but I just did some real simple logic and literally added one equation to my model, where I said if the temperature of 346, which was my temperature of the outlet, ever drops is less than the temperature of the tank node that had my tank, my 100 gallons of water, then turn off my flow conductors, set them to 0. And this is a Fortran 90 style equation where it takes this conductors from 3728 to 3868, that whole range of conductors, and just set them to 0 without going through a do loop. It'll just do it in that statement. And I could look in my Patran generated model, and it documented that these were my flow conductors, so I could see exactly what these numbers were, and then I just had to drop in this line of equation, and then I got this performance here with the turning off. I want to say a little bit about contacts, because thermal contacts are very important, spacecraft models and also in terrestrial models. There's PC boards and things. You might have edge to surface or edge to edge, or chips on boards that are surface to surface. So we can model an edge to edge contact like you see here, a surface to surface like you see here, or an edge to a surface. And these contacts are shown as little bar conductors, but these are automatically generated by our translator that goes between Patran and Sinda, and they're done at runtime. So if I decide to move this big cylinder block somewhere else, move it over here, and then I run, it will do the hookup over here. So it will project one surface onto the next, even if the meshes don't line up, and it will hook up the nodes as best that mathematically can be hooked up, depending on the mesh, and it will do that all automatically. And we have a post-processing way of visualizing what those hookups were. And so whether it's a conduction hookup like this, or you have airflow over something with convection down to the surfaces, or internal airflow, it's very easy to set up these contacts. You just basically say this region or this edge is hooked to this edge, or this surface of this tube is hooked to this line of nodes that model my airflow through it, and we automatically generate all those little spider web convection conductors or conduction conductors. So it's really as simple as we say 1, 2, 3. The first step, you pick for convection, advanced convection, you pick your fluid like air or water, and you can have temperature-dependent properties, and these are all maintained in an Excel spreadsheet that you can have your own libraries of materials in Patran. And in this case, these are fluid materials. You can set the units that you want to use, and then you pick the convection correlation that you want, whether it's forced or natural or internal forced or external forced, and then you attach it to the surfaces, and you do this at a geometry level. So even before you mesh the part, you just say this surface is attached with this correlation to this airflow or this node, and it will model something like natural convection here, where we have natural convection off this PC board, and we're getting a maximum of 55 degrees C, and then we changed it to airflow over both sides with a certain mass flow rate on internal airflow, like between PC boards, and now that dropped with that particular airflow, it dropped the temperature down to 42 degrees. I want to look at now a different application, spacecraft in orbit that has a lot of radiation involved. And we have lots of ways of doing radiation. We can do it off of individual flat plates, finite element mesh, but we also have abilities to in Patran to create true geometric surfaces, like a round cylinder here and a disc or a sphere or a parabuloid, and we can put a simple mesh on it. In this case, it's an AB mesh. I just said mesh the cylinder one around and one down. So the radiation mesh can be different than the conduction mesh. We may have a fine conduction mesh, but a large radiation mesh, or they can match if you want, but you don't have to have the radiation mesh that goes off to Thermica be one-to-one with the conduction mesh. So we have different ways of doing that. We also now have a new feature where we can have different enclosures and rerun just one enclosure or another. Like in this spacecraft here, this like Hubble telescope looking at stars. You could have on the inside where everything sees everything, you can maybe use, especially if it's an enclosure on a satellite where it doesn't see any solar flux, you can use SindaRAD, which is a fast hemicube method, runs on parallel cores, and will compute hundreds of millions of view factors very quickly. And then on the outside, where you need solar flux and specular bounces, you could use a ray tracing code. So different enclosures can have different methods, and that's all part of Sinda 2012 and our Patran 2012. Thermica transparently integrates and lets us visualize the object in orbit and then post-process different results such as absorbed solar flux or incident planetary flux, and then brings all the temperatures and all the data back into Patran, where you could then do thermal stress or something with Nastran if you wanted. Before I drop into Patran for a quick demo, I want to just talk about an automobile application of Sinda, and that's a muffler here, and we have exhaust flow through here with convection to the walls, and we have a radiation shield here trying to protect the passenger's feet from that hot exhaust pipe. And we have a view factor program called SindaRAD that can compute, in this case, about 1 million view factors in 5 seconds, and you can go into it and actually look at view factor from one surface to another. And then we're modeling convection down through this exhaust pipe also in this model. So let me take just a few minutes here and pull open Patran. And here's this exhaust problem here. And inside this, I have some airflow, which is just a bar conductor, and that bar conductor was hooked to all the surfaces that formed the exhaust pipe, and these these conductors were automatically computed that hooked up the airflow to the surrounding walls. So all we did is say hook up this line right here of bar elements, hook that up to the surfaces around it, and it automatically found the closest neighbor and did all the HA convection conductors for us. So let's go back and look at this the exhaust pipe itself and the plate, and I'm going to run it just to show you how fast this actually runs. And on this model here, on the thermal setup, I'm using for the radiation solver, I'm using what we call SindaRAD, which is our high-speed Hemicube method. And I also decided to check this box to run it interactively. So it's going to pause in the middle of SindaRAD instead of just automatically running, so I can show you what the view factors look like. So it first builds the radiation model, and I can come into here and see this model that it's generated. All the radiating surfaces are shown here, and I'm going to compute the view factors, and it's computing here, and it's using all 4 cores on this processor, and it just computed 926,000, almost 1 million view factors. Now I can right-click on a surface and see the view factor from that surface to other surfaces. So I can just double-click on anything and see from that surface how well it sees other things. And this is especially important if you have some electronic equipment you're trying to shield from something hot. You can just kind of play around with your geometry and see what can see what, and if the shield's working or if there's something hot that has a good view of something that you're trying to protect. But then when I'm done with this, I just close it and say save it, and it will fold those results into the Sinda model, and then it runs Sinda, which runs it's running right now, steady state solution, and it's completed. And I can access my results and come over, well, I'm post-processing now, but I can then pick my run here, or if it's transient, my time step, and hit apply and see my color isotherms. I'm going to just quickly drop into one other model here, the Spacecraft model, because I want to show the link, transparent link to Thermica and how that plays together. So we have a spacecraft here, which was just a cylinder, and I did this primitive radiation. The cylinder was built as a primitive. We have modeling techniques in here called P-shapes, where we can build things out of primitives, and we can actually edit and change their shapes, and the mesh will rubber band when you do that. But this mesh is for conduction only. You may have a radiation mesh that's actually very different. It may be only 1 by 1 on this cylinder, and maybe only 1 by 1 on that disk, and then we end up taking absorbed heat flux into that larger radiation shape and breaking it down using some advanced algorithms to proportion it more correctly to the different elements. So when we go to run this here, and I come under my thermal setup, and I pick either steady state or transient run, and then because this is involving radiation, I have to pick what radiation solver I want to use, and I have Thermica V4, version 4 selected. And so now when I run, it needs that thermal loads from the orbital heating first before it can solve the problem. So it first drops us into Thermica with my model here, and now I can come and load whatever trajectory and whatever kinematic laws I want. And I'm just going to load this one mission here because this will load all my files for me. And what I'm going to solve in Thermica are just 3 processes here. I'm going to solve a radiation process to get my view factors, specular and diffuse. I'm going to solve for my solar flux and for my planetary flux. And these all have lots of options. The planetary flux has different models for different planets with hot the hot side and the cold side and maps those temperatures, or you can do your own planetary maps. There's a lot of sophistication to this, but basically we have our orbit, and I'll fit that trajectory. We have our orbit. We have a kinematic law which has our solar panels tracking the sun, and we can review that law, play it back on our trajectory, and see the y direction here of the solar panels is pointing towards the sun, or doing the best job it can pointing to the sun, with the body of the spacecraft pointing towards the orbit velocity vector and the planet. In 1 degree of freedom here, it would do the best job it can. We can actually look at that pointing error. And then we can look at our mission here, and our mission will fit the trajectory, and we can see our spacecraft in orbit, and I can actually fit the model in the sun's back here. You can see shining on the other side, and I can lock my camera on the model, or on the model orbit frame, and now the animation may not work too well on the WebEx, but I'll animate this, and the solar panels are moving to track the sun as we're going around the Earth. And this is just my geometry after I run my processes here. Let me just run and do the computation, which takes maybe less than a minute. And as this is running, I can pull up my monitor, and you can see it's running on all 4 cores on my quad-core machine here. So Thermica runs in parallel. Our SindaRAD fast Hemicube code also runs in parallel if you have a 4-processor machine, or 8 processors, or 2 processors that run faster. And it's computing all the solar flux, view factor, solar flux, and now the planetary flux. And it's using a pretty complex sun model. When you get close to the sun, the rays come off at different angles. Now we're all done. So now, once you have these results, we can actually come back into our mission module here, and we can post-process on the model and look at our results. We can look at things like alpha or epsilon, or some of the view factors, but we can also look at the absorbed solar flux. And you can see here it shows the absorbed solar flux is 1,072 is the peak, or that's the absorbed solar flux, as opposed to direct solar flux, which is 1328. We can look at Earth, the albedo, or we can look at the which is 257, the absorbed albedo, or we can look at the absorbed Earth planetary flux also. So we can look at the different components, and then we can also animate that and look at it as it goes in orbit. And we can even make a movie of this by hitting the record button, and the movies can be even video recording. You see here, you can even make a 1080p movie that's widescreen, MPEG-4 movie of your results, of any of the results that you've computed, including visualization of ray tracing if you want to see what that is. So when you're all done here and you've computed all your information, you can then basically get rid of Thermica, and it goes back to Patran, and will continue to solve and bring in the results. Now it's pre-processing, and then it actually ran very fast because it was a pretty simple model. So that concludes my presentation, and I think Srinivas, will come back to you. You're taking questions via the panel. I think they can ask questions.
Yeah, thank you very much, Ron.